Welcome to Module 1 of our Piping Stress Analysis course. Today, we're starting one of the most important topics in piping engineering, piping stress analysis. If you're new to this field, don't worry, this module is built for you. We're going to explain in simple terms what forces act on a piping system, what makes a system safe, and how engineers decide whether a detailed stress analysis is even needed. By the end of this module, you'll understand three things: what piping stress analysis actually means, the three conditions every safe piping system must meet, and the industry guidelines used to decide when formal analysis is required. Let's get started.
So, what exactly is piping stress analysis? In simple words, it's the study of every force and load acting on a piping system, checked against the worst case or critical conditions defined by the design code to confirm the system is safe as designed. Think of a pipe like a bridge. A bridge doesn't just sit there doing nothing. It constantly carries the weight of cars, wind pushing against it, and it expands and contracts with temperature changes. A piping system is no different. It's constantly being pushed, pulled, stretched, and loaded by multiple forces at once. Stress analysis is how engineers make sure the bridge, in this case the pipe, can handle all of that without failing. Let's break these forces into two groups, exactly as shown on this slide. First, vertical loads. These are gravity related. Gravity is always pulling down on the pipe, and it comes from four sources: the weight of the pipe material itself, the steel or metal, the weight of the fluid flowing inside it, water, oil, gas, whatever the pipe is carrying, the weight of valves and fittings, elbows, T's, flanges attached along the line, and the weight of insulation and the supports holding the pipe up. All of this weight pulls downward, and the pipe supports must be strong enough to carry it. Second, we have the other forces column. These aren't about gravity. They're about pressure, temperature, and the environment. Internal pressure, the fluid inside is pushing outward against the pipe walls. Thermal expansion and contraction. When hot fluid flows through a pipe, the pipe metal heats up and grows longer. When it cools, it shrinks back. This constant growing and shrinking creates stress. Wind loads. For pipes running outdoors, especially on tall pipe racks, wind pushes against them. And seismic or earthquake loads. In earthquake-prone areas, the ground shaking can impose sudden, severe forces on the piping. So remember this simple idea. A piping system is never at rest. It's always fighting gravity, pressure, temperature change, and sometimes wind or earthquakes all at the same time. Stress analysis is how we prove mathematically that the pipe can survive all of that safely. Now that we know what forces act on a pipe, let's look at what conditions actually define a safe piping system.
For a piping system to be considered truly safe, it must satisfy three separate conditions. Let's go through each one carefully, because this is the foundation of everything else in this course. Condition 1, strength. This means the pipe must be able to withstand the applied forces we just talked about, weight, pressure, thermal loads, without the stress inside the pipe wall exceeding the allowable limits set by the governing code, such as ASME B31.3, which is the code commonly used for process piping. Think of strength as answering the question: is the pipe material strong enough to not crack, yield, or rupture under the loads it's experiencing? Condition 2, flexibility. This is a little more subtle. A pipe carrying hot fluid will expand as it heats up, sometimes by several inches over a long run. If the pipe is rigidly restrained and can't move at all, that expansion has nowhere to go, and it builds up enormous internal stress, potentially enough to crack the pipe or damage supports. So the piping layout, the bends, loops, and routing, must be flexible enough to absorb this thermal growth naturally, like a spring, while keeping the resulting stress and movement within code allowable limits. Engineers actually balance strength and flexibility against each other. Too rigid and thermal stress becomes dangerous. Too flexible and the pipe may sag or vibrate excessively. Condition 3, equipment nozzle loads. This condition is often the most overlooked, but it's critical. Pipes usually connect to equipment, pumps, pressure vessels, compressors, through connection points called nozzles. These nozzles are delicate. In fact, as the slide points out, pump nozzles typically can only handle less than 5% of the load that the connecting pipe itself could handle. That's a huge difference in strength.
So even if the pipe itself is perfectly safe, if it pushes or pulls too hard on the equipment nozzle it's connected to, it can damage the pump, vessel, or compressor, leading to leaks, misalignment, or even equipment failure. That's why engineers specifically check nozzle loads against the equipment manufacturer's allowable limits, which are usually much stricter than the pipe's own limits. So to summarize this slide in one sentence, a safe piping system must be strong enough to survive its loads, flexible enough to absorb thermal movement, and gentle enough not to overload the equipment it's connected to.
We just learned that equipment nozzles, like those on pumps and compressors, are extremely sensitive, capable of carrying less than 5% of the load the connected piping could otherwise handle. So what do engineers actually do about this in real-world designs? This slide shows two common solutions. Solution 1, expansion joints. An expansion joint is a flexible connector, often made of metal bellows or a similar flexible material, installed directly between the piping and the equipment nozzle. Picture it like a flexible accordion-style joint. Its job is to absorb thermal movement and vibration before that movement ever reaches the sensitive equipment connection. This solution is especially useful in situations where you simply can't reroute the pipe, for example when space is tight or the layout is fixed and there's no room to add more bends or loops for flexibility. Solution 2. Support relocation. Instead of adding a flexible joint, engineers can also solve the problem by changing where and how the pipe is supported along its route. By moving a support to a different location, or by changing the type of support, for example from a rigid support to a spring support, the load path changes, and the forces get redistributed away from the equipment nozzle and onto the supports instead, which are built to handle those loads. This is typically figured out during the stress analysis process itself, using specialized software that models the entire piping system and calculates exactly where the loads are going. So, in short, if a nozzle is being overloaded, engineers have two main tools: add flexibility right at the connection with an expansion joint, or redirect the loads elsewhere by relocating supports. Often, real projects use a combination of both. Now, naturally, the question is, does every piping system need this level of detailed stress analysis? Let's find out.
Here's an important truth about piping stress analysis. There is no single universal rule that applies to every pipe in every plant. It always comes down to the judgment of an experienced stress engineer. However, the industry has developed widely accepted guidelines to help identify which systems are likely to need formal analysis. Let's go through all 6. 1. Large diameter. Any piping system that is 12 inches in diameter or larger is generally flagged for stress analysis. Why? Because larger pipes carry more weight, more pressure, and generate larger forces at supports and equipment when they move. 2. Hazardous fluids. If a system carries hazardous, toxic, or high-temperature chemicals, the consequences of a failure are much more severe. A leak isn't just an inconvenience, it could be a safety or environmental incident. So these systems get extra scrutiny regardless of size. 3. Complex routing. If a pipe has a complicated layout, or if it's a short run that's rigidly anchored, meaning fixed, at both ends, it has very little room to naturally absorb thermal expansion. That combination often creates high stress concentrations, so it needs to be checked. 4. Rotating equipment. Any pipe connected to pumps, compressors, or turbines needs analysis, because as we covered on the previous slides, this connected equipment has very sensitive nozzle load limits. 5. The 1500 rule. This is a quick screening formula. Multiply the pipe diameter in inches by the temperature differential in degrees Fahrenheit. If that number is greater than 1500, a formal stress analysis is very likely required. We'll look at this rule in much more detail on the next slide because it's used constantly in real practice. 6. Engineer judgment. And finally, regardless of what any of these rules say, an experienced piping stress engineer always has the final say. These guidelines are useful screening tools, but they don't replace professional judgment. A system might technically pass every rule above and still warrant a closer look if the engineer sees something concerning. Let's now zoom in on that 1500 rule, since it's one of the most commonly used screening checks in the industry. This slide focuses entirely on the 100-50-100 rule, a fast, simple way to screen whether a piping system likely needs detailed stress analysis without having to run full software simulations first. Here's how it works. You take two numbers. First, the pipe's diameter, measured in inches. Second, the temperature differential, measured in degrees Fahrenheit. This means the difference between the pipe's operating temperature and its installation, or ambient temperature. This temperature difference is what drives thermal expansion. Remember, the bigger the temperature swing, the more the pipe wants to grow or shrink. You multiply these two numbers together, diameter times temperature differential. If the result is greater than 1500, formal stress analysis is very likely required. The combination of pipe size and thermal movement is large enough that the system probably can't be assumed safe without checking. If the result is 1500 or less, analysis may not be strictly required. But, and this is important, the engineer must still confirm this. This rule doesn't automatically clear a system. It just tells you it's less likely to need in-depth analysis. Let's do a quick example to make this concrete. Imagine a 10-inch diameter pipe with a temperature differential of 200 degrees Fahrenheit. Multiply 10 by 200 and you get 2000. Since 2000 is greater than 1500, this system would very likely require formal stress analysis. One final and very important note, which the slide itself emphasizes, this is a screening rule only, a fast first check, not a final answer. The ultimate decision always rests with a qualified piping stress engineer who will consider this rule alongside everything else we've discussed: diameter, fluid hazard, routing complexity, and connected equipment. Let's now bring everything together with a quick summary of what we've covered in this module. Let's recap everything we've learned in this first module, point by point. Point 1. Stress analysis studies all the forces acting on a piping system to confirm that it is safe. Point 2. These loads include gravity, meaning weight, internal pressure, thermal expansion, wind, and seismic forces. Point 3. A system is only considered safe when it satisfies three conditions together: adequate strength to resist the applied forces, sufficient flexibility to absorb thermal growth, and acceptable loads at equipment nozzles. Point 4. Equipment nozzles are the most sensitive part of the system. Engineers must design carefully to keep forces at these nozzles well within the manufacturer's allowable limits. Point 5. Several industry guidelines help identify when formal analysis is needed: a diameter of 12 inches or greater, hazardous fluid service, connection to rotating equipment, and the 1500 rule we just calculated together. Point 6. And ultimately, no matter what the guidelines say, it is always the experienced piping stress engineer who makes the final determination for every individual system. That brings us to the end of Module 1. In the next module, we'll go a level deeper and explore the classification of loads and their effects on piping systems, building directly on the force types we introduced today. Thank you for watching, and I'll see you in Module 2.